I welcome all of you to the first international conference or first international workshop on the big data analytics for the sustainable environments. Here is the agenda for today's workshop. After my welcome session, we will be having a talk. As you already know that SK Reddy is going to give a talk on the predictive maintenance for Industry 4.0. I will come to this later. First I will introduce rest of the agenda. So after SK Reddy's talk, we will have one more talk from one of the authors of the paper, and then we will have a short coffee break from 11 to 11:30, right? And then we will go downstairs where the coffee and all the arrangements are, and we will be heading back to this workshop again at 11:30. Then at 11:30 we will be having 3 different talks on different research papers, and then the lunch will be served at 1 o'clock again downstairs where we'll be going for the coffee. One thing which I haven't mentioned on the website, after the lunch break we will have a keynote speaker downstairs in the main auditorium. That talk will be for 1 hour after the lunch break. So after the lunch break we are not coming to this straight. For 1 hour we will be downstairs for that auditorium talk. That will be finished at 3 o'clock, and then at 3 o'clock we will come back again to this workshop where we will be having 3 more research papers, and we will finish our talk or this workshop around 5:30. Yes, so all this information is available on the website. If you can go to the UCC website, and then you will see the details about the workshop. You can see the website for the PDASE, and then you can download the agenda from there. So little bit about our prestigious guest speaker here. His name is SK Reddy. He just said it was hard for me to pronounce, and he said just say SK. I'm fine with that.
That'll be a test for you guys too. After the presentation, you have to tell my name back to me. Karunakar Reddy.
Karunakar Reddy. So Karunakar Reddy is going to give a talk on the predictive maintenance for Industry 4.0. Karunakar is the Chief Product Officer Artificial Intelligence in Hexagon. He is an expert artificial intelligence master. He is also a very successful startup entrepreneur, if I'm not wrong. Yes. And he is a very good advisor for artificial intelligence startups. He writes his own blogs related to artificial intelligence. You can find on the LinkedIn. Actually, I searched yesterday. He has put large number of blogs on the LinkedIn, which I just went through quickly. So you can follow him on the LinkedIn, and you will find a lot of his blogs over there. And I think he loves to speak in the conferences. So yeah, a little bit about SK Reddy, and maybe he will introduce himself later on. Thank you very much, SK.
Thank you.
Hand over to your talk, please.
Thank you very much.
Thank you.
Can I move your laptop a little bit from to this side? Good morning, everyone. It's morning 9:15 on a Monday, so I think there should be a little more energy in you guys. So let's say one more time. Good morning.
Good morning.
Okay. I'm going to talk about predictive maintenance for the next 45 minutes to 1 hour, and I don't think I'll have time for questions too. But you're more than welcome to interrupt me and then ask me any questions you have. Artificial intelligence, I think, is really picking up, and so many companies are adopting AI in their respective world. Industry 4.0, all types of companies are using AI for so many different purposes. Of course, predictive maintenance is one of them. I'm going to talk about a couple of fundamental topics about predictive maintenance, then jump into some advanced topics in predictive maintenance and how companies are trying to solve some of the prediction related problems, And then I'll also talk about how the pipeline, the infrastructure that's required to set up in the company to manage the predictive maintenance solutions. Before I get into the topic, I really want to talk about how AI is making a fantastic impact. Some of the use cases being solved almost sound like impossible sounding use cases. And I like the word impossible. Do you like the word impossible?
No.
It's not a trick question. Okay, let's try that. If I give you a random number, a 4-digit number, a 5-digit number, and then ask you to memorize it and repeat it back to me, you would do that with not much of difficulty. Let's say the random number is 78453, you would remember that. And if I give you a 6-digit number, maybe with a little bit of effort you can memorize it and then repeat it. If I, let's say, give you a 10-digit number, which is typically, I think, your telephone numbers, it takes a little more effort for people to memorize a 10-digit number. Do you remember the telephone number of your girlfriend, boyfriend, spouse, mother, father? Because it's already stored in your phone, right? You don't need to remember. Push that number 10 to a number which may be impossible sounding number. If I give you a 50-digit number, even if I give you a 1 hour time or even 1 day time, would you memorize it and repeat it? Maybe with lots of effort. Yeah, if I say I'm going to give you $1 million, I'm sure I think that motivates people to do. But let's push the number from 50 to something even more impossible sounding. How about a number, 100-digit number? You know the world record is 432 digits. A person from Mongolia, actually there's a world record he has set up, he could recollect a number with 432 digits in it. So anything which says sound impossible initially, it's not any more impossible. And AI is actually proving multiple times in the organizations, many organizations. Before I get into some solutions, have you seen these two pictures on the news in the recent past? On the left side, that's a painting which got recently sold. Christie sold a painting. They thought it's going to get $7,000 to $10,000 US, but actually got sold for $432,000, close to $500,000. But that's not the big deal. The big deal is the painter is not a human painter, it's an AI model which has painted the image. $500,000. And the one on the right side, I think it's even a little more popular. The famous Chinese news agency, I think, has come out with an AI NLP model which actually collects the information, processes the news, and also speaks the news as if it looks exactly like a human being. These were, I think, at least a year ago, I think it's very, very impossible sounding possibilities, but I think AI is doing it. Let's talk about big data. Organizations have come a long way. There's a lot of maturity has come in the organizations. On the left side, you actually have the organizations which are focusing on the data warehousing or extraction and loading of data, but companies have started focusing on business intelligence or even agile business intelligence. And of course, off late, companies are focusing on predictive analytics. And the maturity actually has to improve in the organization. Not only you have to be aware of what data to be collected and store it and pre-process it, also not just run dashboards in the organization, but eventually you have to use this data to predict what's going to happen in the future. And that's what many companies are doing, and including Hexagon. And the term big data, I think, is a little confusing term. People, I think, talk about big data and define big data in different ways. For ease of our today's discussion, let's say big data is that possibility of massive amounts of data which even BI tools, business intelligence tools, cannot process anymore. And sometimes there is wisdom in this data which a regular BI tool cannot figure out. That's when you use machine learning techniques or even deep learning techniques to process the data and figure out what is happening and then make sense out of it. So in this whole world of data management or data science, if you look into, there are multiple skills that come into the organization. So if you are a data scientist, or if you want to become a data scientist, or if your organization is trying to go on the path of data science or data management, or trying to do some predictive maintenance or predictive analytics in the organization, people need to understand the interface of statistics and operations research and machine learning. Some very, very absolute fundamentals of predictive maintenance. predictive maintenance is nothing else but trying to figure out some sort of anomalies, some type of outlier, some type of irregular behavior, something which is not normal. All of these explanations explain predictive modeling. I will be explaining a couple of use cases, a little advanced use cases, which have been recently published, and 2018 papers published, which talk about how to predict what's going to happen next. I live in Silicon Valley, and there are a good number of startup companies which are investing money on predicting who's going to win the next ball game, or if it's a football or whatever game is going to happen, basketball. But that's, of course, beyond the discussion today. But anomaly detection can be anything which is not normal, which is not common, what you normally don't see. But again, you have different types of anomalies. For example, in the context of this entire global information of what you have, X2 and X1 could be anomalies. You can say, oh, that's completely out of the mark. But sometimes it could be the C2, the cluster C2 itself could be off the norm. That may not be what you normally expect. And you also have local anomalies and global anomalies, and I explained just now the global anomalies is X1 and X2, but local anomalies can be X3. Within the cluster of C2, X3 can be an anomaly which I think need to be identified. So in the global context, you not only identify the cluster that falls outside the normal realm, and within that you start identifying what's an anomaly. And machine learning techniques are available to define that. The most commonly used machine learning methodology to do predictive modeling is just plotting the information on a multi-dimensional graph and identifying some definition of an outlier, some irregular behavior, something which doesn't fall into the normal thing. For example, in this picture, you have two major clusters. Your point of interest, an anomaly, can be any of these small points which are distinctly far away from the cluster. How would you know? You actually can find out the nearness index, the L1 index or L2 distance, or any other, even cosine similarity, to identify if these all vectors falling into this cluster have certain nearness distance index, and what will be the distance index of those factors. That's one way of detecting. But then you're using only the points. And there's not just a one-dimensional point, it can be an n-dimensional point. For example, if you have a vehicle maintenance problem in your organization, and if you want to predict when the vehicle is going to break down in the next, let's say, 1 month or 1 week or even 6 months, the vehicle can break down not just because of the overusage or overheating of the engine, it could be so many other factors too. So if you create a vector for one vehicle, that vector would be an n-dimensional vector. N can be anything from 2 to even 500. Normally you find around 100 to 150. More than that will be computationally expensive, but many organizations, many solutions, I'll talk a couple of them today in the presentation, the dimensionality of a vector could be around between 10 to 50 or even 100. At the same time, there is good amount of research happening on graph-based anomaly detection. When I say graph-based anomaly detection, the logic that graph-based connects is if you have one anomaly doesn't exist in isolation. There may be things that are correlated. For example, if you want to find out the anomaly of a fraud feedback about your product, it's just not, maybe that person who's giving a fraud feedback might have given similar feedbacks of different products, and they're all connected with each other. So on the left side, if you focus on the point-based outlier detection, you are making an implicit assumption that that point exists on its own. The influence of the others may not be that high, even though you can translate the influence of other factors into a single vector, but there is a good amount of focus on the graph-based analysis too. There are around 5,000 machine learning and statistical techniques available that will help organizations predict the maintenance issues or how to predict what's going to happen. 5,000. And it's humanly not possible for a single person to remember all of them. And all of these techniques, they respond differently. So I actually picked up a report where a bunch of ML scientists picked around 17 different techniques and used the same 17 different techniques on exactly the same 10 data sets for the same use cases. If you're applying multiple different techniques on the same use cases, on the same data sets, and if you look at the responses, then you would know which technique seems to be performing better than the other, and then you can pick one instead of memorizing or understanding the 5,000 different techniques. Let's talk about some of those techniques, especially the unsupervised anomaly detection algorithms. These are around 12 to, I mentioned here 12, but I think around 17, the report, which is mentioned at the bottom of the slide. You can get that information later too. They picked 17 different techniques and looked at 10 different data sets. And these are some of the techniques they were focusing on. You have the k nearest neighbor or kth nearest neighbor or local outlier factors or even clustering based multivariate Gaussian outlier score. There are so many different techniques that could, even the most popular one class SVM. I remember a couple of years ago when I was working for Apple, Apple had at that time in iTunes around 800 million customer credit card details or customer IDs. And there were transactions done by these customers, either in terms of app downloading or song downloading. Let's only focus about song downloading. How would you predict certain behavior is an outlier behavior? We just did not know how to predict what's the good behavior and what's the bad behavior. Also, if you know, in credit card fraud transactions, if there are billions of transactions happening on a daily basis or a weekly basis, the percentage fraud transactions are extremely small, 0.001. Maybe I think in a billion transactions, maybe 100 or maybe 1,000, maybe 10,000 transactions could be fraud transactions. But in the context of a billion transactions, there's an extremely small percentage. So the most common machine learning technique being used for predicting anomaly is SVM, single support vector machines, and that too one class. So train a model on one class, and anything falls outside that class is an abnormality. That one class happens to be the normal class. So in that billion transactions, 99.9999% of the transactions are valid transactions. Create a model that will understand what is a valid transaction. And then every time a new transaction comes in, give the transaction to the model, and model will tell you whether, this is the regular model regular transaction I've seen, and if the regular transaction, then you just let the transaction go through, and if it's outlier, then I think you reject the transaction. So that's what we did in Apple, where we were not sure how to detect an abnormal behavior of downloading, so we actually used it for one method was one class SVM, but we also had an ensemble. Ensemble is a technique many machine learning companies use, where instead of using one particular method, you actually use different methods, and the answer by each of the method is averaged out to make a final prediction. Anyway, coming back to this point, in this research, the 17 different techniques on the same 10 data sets, when they were published, when you analyze them, for example, on one particular data set, on breast cancer data set on one side, the area under curve, I think, dramatically dropped when the K value, the number of classes, the number of the K value is less than 10. So in the kth nearest neighbor or K nearest neighbors method, if you are trying to do the K value, pick anywhere between 10 to 50. Anything more than 50, I think it doesn't even make sense for you. Anything less than 10, model cannot understand better. But this is the more interesting one. If you look into some models did not even perform at all, and some other models really picked up well. So the summary in this report is there are certain techniques which really perform well on the local factors, and some models perform well on the global factors. In other words, if you have, let's say, a predictive maintenance or let's say anomaly detection for intrusion detection on your network, if you look at the org-wide intrusion detection problems, and if you want to find out any hacker trying to intrude, the global level certain techniques actually work really well. But if the hackers are targeting a specific server or a specific geography or a specific division, then certain techniques actually work on the local factors need to be applied. For example, the local outlier factor, connected to base outlier factor, these are some of the methodologies or techniques which work at the local levels. But the most interesting part is this. For the same 10 data sets, then the 17 techniques, all of them responded differently in terms of accuracy, deterministic, sensitivity, speed, global detection. Some models are really good in global detection and some are extremely bad. Some are very good on accuracy levels and some are not at all good. And while the accuracy levels are higher, the deterministicity and sensitivity is when you change the data a little bit. How quick is the model to understand and pick up quickly what is the abnormal situation there? All of these models responded differently. So my opinion is, as a data scientist, to define certain predictive modeling in your organization, you can pick any technique you want based on your familiarity and the ease of availability of the solution for that. The most important, of course, is the data set availability, but the second important would be designing a model, I think, would not be that difficult compared to figuring out what model or what technique that need to be adopted. So if you want to adopt a k-nearest neighbor or the Gaussian methodology or single class SVM or a two class SVM, the real intelligence of a data scientist comes in to find out which methodology or which ensemble of methodologies need to be picked up. That's in terms of the numeric predictive analytics area I want to talk about. I want to switch gears and then talk about really complicated problem statements in companies. For example, if you're at a construction site, you want to find out something irregular going to happen. Or let's say you are a smart city situation where you want to track, you have surveillance cameras and you want to find out something that's going to go terribly wrong in the near future. Deep learning has been helping to solve many of these problems for some time. In 2012, the first paper published using CNNs for image processing came out. And within 3 years, that is 2015, the accuracy of models detecting and analyzing images crossed human performance levels in 2015. And that was around 3.6% was the accuracy, the error rates of models, whereas human error rates are around 5 to 6%. And 2016 came down to 3%, and 2017 it came down to 2.6% approximately. So deep learning is being even used today, but there are other techniques that have come which are part of deep learning. For example, GANs, generative adversarial networks, which are you familiar with the term, GANs? GANs are being used, for those people who are not familiar with, these are two different networks, neural network, which will start creating something, let's say in this case an image, and the other network will look at the output and then tries to cheat or create something else and cheat the first model. And this duel of back and forth between the two models actually goes for some time, and the model, the network can create a solution which actually perfects all the input conditions that goes into the image. I think it's 2017 or 2016, I think NVIDIA published a paper. I had a quick small test for you guys. There are 8 images on the screen. Which images are fake images? Not a real human being. Give me the numbers. It's more than one.
Number 8.
Number 8, okay. Isn't he Michael Douglas?
Huh?
Isn't the guy in number 8 looking like Michael Douglas, the famous Hollywood actor? But never mind. We'll take your number 8, okay? 1, okay. 1 looks too perfect, right? It's too perfect and too symmetric. Yeah. I get that. Because everything is symmetric there. Yeah, you're right. Any other? No tags for predicting. Go ahead, predict. What do you think which one is a fake?
All of them.
All of them? Okay. Who believes all of them are fake? Who believes 1, 2, 3, 4 are fake? No? Okay. The mere fact that there is no uniformity in the opinion of the audience itself shows that NVIDIA or neural networks actually were successful in their game. By the way, all are fake. All are created by a machine. But they were created with inputs of images from real people, and the model actually picks up certain features from certain pictures and combines them to make a single image. I've been doing this testing whenever I present to any conference, and I actually find that. And until now, I think there were 1% or less than 1% of the people actually could consistently agree that it all are fake. And that shows that some of the deep neural networks, and also I think GANs, have really been successful. Let's talk about one complicated solution that is used in your predictive maintenance. Especially this is a solution which is used in airport securities. You have screening, X-ray screening of your checked luggage, and you want to predict something is wrong, or you want to find out if something is wrong in a bag. Also, what is wrong, what is abnormality, I think you cannot define in a finite way. Yeah, having a sharp object, having a liquid, sharp object, or even a battery run device in a checked-in suitcase, I think may be a problem. But the definition of abnormality itself is constantly changing. So here is a multi-neural network methodology. For example, you have the encoder and a decoder together, a GAN, which is taking an image in, processing it, and creating an embedding vector Z, which is nothing else but an excellent summarization or representation of X. X is the input. And the decoder network would create an image based on this Z as a representation, and it creates an image called X cap. And obviously X cap and X need to be exactly the same if the model has been very, very successful, the GAN model is successful. But if you train the model on all normal, regular, acceptable images, X-ray scans, then the model is trying to constantly learn what is an acceptable way of converting an input image into an acceptable representation, and from this representation create an acceptable image. In other words, the abnormalities are normally excluded when you bring the dimensionality down to Z level and then bring it up to a regular image. After that, you create, using this output X and the original image. So now you have images created. The model has understood how to create a new representation of the same image, and it has done it over a period of time. Now it understands how to only pick the normal behavior. But now during inference time, when you give an abnormal image, it picks up and creates an X cap which is not the same normal. And the distance between those two, Z and Z cap and X cap, are part of the loss function which you put in the neural network, which will detect what is normal, what is not normal. More details can be found in the in the paper down there. But the point I'm trying to make is, if you have any type of camera situation, if you want to, if it's a construction site, if it's a defective product, or in the manufacturing location, any item or anything you can see with your eyes can also be seen by an image or a camera, and you can ask the model sitting on the surveillance camera or on the sensor to predict what is normal, what is not normal. A similar advanced deep learning based technique is identifying anomalies using traffic surveillance cameras. And here, it's almost the same approach. You have two networks which look into the same image. One network detects objects using a technique called faster RCNN. Actually, the first technique was RCNN, then came fast RCNN. There was improvisation done. And then after the fast RCNN came, faster RCNN came. That proves that AI scientists are not really creative in naming new inventions. So faster RCNN is used to detect objects. And then another network, you actually do the optical flow. What's an optical flow? If you have a video camera of multiple frames over a period of, let's say, 10 seconds or 10 minutes or 10 hours, frame to frame, if some of the pixels brightness changes suddenly or gradually, normally between one frame to the other frame to the other frame, the brightness changes gradually, and to make the model more intelligent and quick to detect, normally you skip one frame or maybe skip 2 frames and then find out the same pixels brightness. Pick any random 4 pixels, 10 pixels, 20 pixels in frame 1 and frame 3. And then if the brightness changes, then you can localize and focus on that area, and you know something is changing here. That's called optical flow. And you can actually see things moving, and you compare the optical flow and the objects and make a prediction of something is actually going wrong and what is going wrong too. You actually have some sort of a classification going on too. These are the two deep learning based models I wanted to actually talk about, but let's switch gears and then come to a little more traditional predictive maintenance of solutions. For example, predicting when the vehicle is going to break down. There are multiple published reports or published papers available on making predictive analytics. This was an interesting paper I picked up and published in 2017. This is a report from Detroit. City government actually has 10,000 or I don't know, 5,000 vehicles, and these vehicles have different purposes. Some are ambulances, some are police cars, and some are trucks and other stuff. And these are kept for, let's say, 5 years or 10 years, and the city government actually has repair centers and workers, and they want to make a prediction on how long a vehicles need to be kept and what should be the preventive mechanism we should have to make sure that vehicles are in place. So the data collection is very, very simple. You actually collect all the types of vehicles. So you actually have a unique ID for your vehicle and the vehicle-related information, like you see here on the top. The departments and the vehicle make, the year, and all of the stuff. And you also have maintenance logs. Let's say you work in a factory. Let's just take a detour from this use case to a different use case. Let's say you work in a factory, and if you have turbines, pumps, walls, and so many different types of machines in the factory. Each of the machine has its own information, some unique way of identifying a machine. The name of the machine, the ID, the make, and the year of the make, and on some of the information. But you also have the maintenance workers going and maintaining these walls and pumps and so many other machines, and you have a maintenance log. For example, maintenance log can be like a job ID, unit number, work order number, whatever is the information you capture. So you have, let's say, 5,000 vehicles or 5,000 machines in your factory, and over a period of 1 year or 2 years, you end up having, let's say, 100,000, 200,000 maintenance logs. Using this information, can we predict which machine or which vehicle in this case needs extra maintenance or even preventive maintenance, or which vehicle need to be sold off? Part of vehicle maintenance or predictive maintenance, there is a different technique or different use case called computing the remaining useful life. Many times if you have in the factory or in the vehicles, for example, or in the machines, after some time, any amount of maintenance is not of much use. It will start deteriorating faster and faster. And then you constantly compute the remaining useful life, and if you feel the remaining useful life of the machine is really, really dropping, you actually can sell off the machine in the second-hand market. Once you collect the data of the vehicle, the jobs, and over a period of time, all that you do is create a three-dimensional tensor. So look at this. You have all the vehicle related information on this axis, and all the jobs are organized here. And how do you do that? So for vehicle 1, if this sheet is for, let's say, 1st of January, vehicle 1, was there any maintenance done for the maintenance type 1? And if you say yes or no, would be 0 or 1. So for the vehicle and the maintenance log and the over a period of time, if you start logging in zeros and ones, you will have a tensor, a three-dimensional tensor, which captures effectively all the maintenance done for all the vehicles over a period of, let's say, 1 year or 2 years, whatever is the timeline you're looking at. Now, this three-dimensional tensor is nothing else but a mathematical problem where you break down the three-dimensional vector into one-rank vectors. And then you end up actually having 3 types of such vectors for the same three-dimensional tensor, and each of the vector will have some insight into the machine. Additional details, I think you should take the paper, but look at this. This is one type of results they've got. If you plot do an absolute time analysis and also the vehicle lifetime analysis. Let's look at this. This is the absolute time analysis. If you look into the type of machines which have more maintenance logs, you can find the green one. That is the machine which actually has a very high maintenance log. So on a holistic level, you can find out, okay, of all the vehicles I have, of all the machines I have, that particular vehicle seems to be demanding more. And within the maintenance log, the list of maintenance, what type of maintenance issues are really peak? For example, the cab, sheet metal, and PM service, all levels, these 2 system maintenance seems to be more in demand. So that is, if you are trying to order for spare parts, or if you're trying to hire workers who can do additional activity, you should get more people with these skills more, or you should get more of spare parts that will supply this and this. But also look at the interesting part. The data was collected from 2011 to 2017, but even though there was a little bit of maintenance reports, the maintenance effort went up in 2014 and 15 and came down in 16. This is the absolute time analysis. It gives you certain insights, but not actionable insights yet. Look at this. You pick one particular vehicle. What is this vehicle? Let's go to the next one. I'll pick a different one, single vehicle. Freightliner. It had good number of system maintenance issues. This is the distribution of system maintenance. But here is the most interesting part. When you buy a brand new Freightliner, year 1 and year 0 there was no issues. Year 2 maintenance issues went up, 3, 4, and after that it dramatically drops. So if you are trying to buy a vehicle, you know year 2, 3, 4 there will be a lot of maintenance issues, and after that the vehicle will not have any maintenance issues. So your ordering of your spare parts or your skilled human resources, etc., could be planned accordingly. Even from day one when you buy. Look at this too. There's a different machine again. This particular machine did not show much of maintenance issues till 2015 or 16. Let's look at, again for a specific machine, year 1, 2 and 3 are where there are going to be more maintenance issues. So if you have the maintenance logs of a variety of machines, it's not one single machine, different machines, different types of maintenance logs. The same maintenance could happen to different machines. So you can't just only focus on maintenance logs or only on the machines. You've got to have data which is already mixed up. Using the machines and the maintenance logs over a period of time, using this technique, converting them into a three-dimensional tensors, you can easily identify actionable courses of actionable instances based on for either the types of machines or types of logs, which will give you further insights into the spare parts, supply chain, skills, etc., whatever you want to hire. Let's change the gears again. By the way, long time ago, when I was speaking in a classroom, I was asking a professor, how do I know people are really interested in what I'm talking? What if they're just only looking at me, but they're just switched off already, and they're thinking about the exciting coffee break they're going to have, or the lunch break they're going to have, and they want really me to get out of the classroom? He said, find out the body language. If there are smiling and making notes, and even when you walk up and down, the eyes move wherever you go, and then you can see a little bit of a live action on their face, that means they're really paying attention. They're leaning back, no pens open, no laptops open, and once in a while, when they blink their eyes, they close a little longer than they open it. Then it's time, I think, to stop. Have you reached that state? Yes? No?
Definitely not.
It's not? No, I think I'll take a few more minutes to talk about a couple of other use cases, and then we'll have question answers. So I talked about deep learning techniques. First, I talked about the comparative analysis of various machine learning techniques. There are 5,000 machine learning techniques which can be used for predictive maintenance, and not all of them can be implemented. Even the techniques themselves, I think, are not comparable to each other. Next, I talked about a couple of deep learning solutions using image processing and stuff. Now, and I just talked about one predictive maintenance of what you normally find in Industry 4.0, whether it's vehicles or machines. The most interesting, most commonly used predictive maintenance problems are time series. Time series is if some things are happening over a period of time, long time, you have enough information about a machine or a product, and then can you use that information to predict what's going to happen? By the way, that is I live in Silicon Valley. My wife works for Google, so I go to Google office once in a while. Google has been tracking the search statistics for the last 20 years. And you actually can see this live graph in the lobby of Google headquarters. And because the number of searches have gone up dramatically, they have to adjust the scale. That's why you see there's a dramatic drop here and a drop here, but there's not really a drop. They're actually readjusting the scale. Just to give you the magnitude of the scale, 20 years ago when they started to today, the scale has changed 2,000 times. That is 2,000x. But again, every time they adjust the scale, the search seems to be going up. But that's just the complexity of the search, complexity of any time series data over a period of time. Majority of time series data has some external influence which really will not help you in making predictive analytics. For example, if there is a seasonality impact, let's say during summers or during winters, the machines actually are, there's a variation of temperature and hence the machines are responding differently. Or during sale season or Christmas time, the machines are being used for longer periods because you don't have time to do even maintenance, and you actually have used the same machine for longer. So there is a seasonality impact on the machines, and you cannot use time series raw data as is when you're making a time series prediction of what's going to happen next in the machine. For example, you actually have to adjust for seasonality, week of the day, or spikes or holiday or any touch abnormality, and you have to adjust the time series. Here is an example where this is the actual, the red one was the actual from here, but then this spike was because of some seasonality. So you adjust the scale accordingly, and hence you redraw the past information to the new scale, so that this seasonality is eliminated when you're making your predictions. Similarly, I think holiday effect, seasonality effect, etc. you need to adjust. But this is a fundamental data cleanup process in any predictive maintenance. But the problem is that if you have large amount of data, humanly, I think even with the naked eye, you cannot really figure out what's happening. This is an example of battery voltages and current being used by different sensors in some use case, and this is what you typically the data you get. If you plot them, this is what it looks like. If you look at individual sensor over a period of time, look at each of the graph. Each of the sensor actually has some graph where the data, the current consumption, the voltage going up and down is being captured there. With the naked eye, you cannot find out. So I looked at a published report on time series analysis using Turkish electricity data. So this is the raw data you see of electricity consumption in Turkey on this is a daily electricity demand. You see there's a huge amount of spikes and drops even on a daily basis. But over a period of time, if you look at it, let's say from 2000 to 2008, the consumption is slowly growing up. And if you break down the same information on a weekly demand here, so this is a daily and this is a weekly, you can see the same amount of variation happening where there is ups and downs. So by just looking at this naked naked eyes, you will not be able to make a prediction of what's going to happen next. So what do you do first? First, you have to adjust for the seasonality. So if you look into holiday seasonality, you see this was the actual consumption or drop in the consumption, but you adjust, you eliminate the drop or eliminate the spike because of seasonality. As I mentioned to you, seasonality could be day of the week, season, holiday, and any other extraneous situations. For example, there was an earthquake, or there was one of the machines, the turbines was down, and hence there was electricity supply was not there, or one grid broke, and hence one city in Turkey, I think, did not even have access to electricity. And if you track the consumption that day, it looks like consumption dropped, but it's not really a drop, but because of some extraneous reasons. So you have the daily information cleaned up here, and you also have the similar cleaning up of the weekly information. So the red ones are the actual consumptions, but you actually create the green ones, which are more of the used for creating a model. In this report, you can find additional information in that link there. The researchers actually used an ensemble of models. So the data was from 2000 to 2006 was used, and 2007, 8, 9, they created an ensemble model which is starting to predict what is happening. Each of the line is a different technique, and the summary or the average consumption is this dark red line. There are different models, and as I mentioned earlier, again this proves the point. one technique is not consistently performing the best. Different techniques performs differently, and this is the problem. Many instances when you actually do a predictive maintenance, you would have to be using ensemble model. And if you juxtapose this information to the real consumption, so from 2000 to 2006, this was a real consumption, and the model was created based on this information, and the prediction and forecasting was being done between this period. The light red color, which is just like a shadow thing, that was the combination of all models together, and the deep red is the forecasted, which is the average of all the ensemble models, and the observed one too, which is actually right here, this black. So you have a green and a black and a red, and you can see the black one. The model, the average model was performing decently well. After having the solution, as I mentioned earlier too, when I started the presentation, I talked about impossibility. When you look at this type of information, and if you're asked to make, can you predict what's going to be the consumption in the next 1 week or next 1 day? It's almost impossible. You have things going up and down. There is no regular behavior happening there. And that's where machine learning models comes to our rescue to actually make a good predictions. This is on a daily basis. And look at the model predicting on the forecasting and the observed, the real data, the real consumption is very close. Okay, let's quickly change gears and then talk about what type of infrastructure you need to have. There's lots of information on these slides. I will not explain each and every point. This and one more slide. When you have a prediction model, prediction models are based on huge amount of data that's coming in. So you have the data acquisition, data persistence. You actually have to store the data and process the data. The model, the predictive model you're creating is only one small piece of the entire solution. How are you going to focus on the data acquisition part? For example, Kafka, a streaming system which can actually, a fault-tolerant streaming system can actually take data at a very high speeds. If you have, for example, in any of the data consumption, or let's say wind turbines or your machines, if you have, let's say 1,000 pumps, on a daily basis, you may be getting so much of data. By the way, when an aircraft takes off and lands after 5 to 7 hours later, and each of the sensor in an aircraft is sending data, how much of data is that aircraft creating, that one aircraft creating in that single trip of 5 to 7 hours? Do you know how much of data it's creating? 1 terabyte. 1 terabyte data is being created just in one flight, and how many thousands of flights are taking off on a daily basis in this world? And having a very effective, fault-tolerant, high-performing data acquisition tool. There are a lot of tools, but I think Kafka is one of the popular tools which actually collects it. And of course, Hadoop is the most common fault-tolerant, horizontally scalable, data persistent model which actually can store your data. But the most interesting part is Spark, Apache Spark, is the system which actually can help you process the information. Apache Spark comes with 5 different modules. One of them actually is MLlib, machine learning library. If you want to develop predictive maintenance models, Spark not only helps you message the data and help you in the processing of the data, you can use some of the MLlib modules available to create your predictive maintenance models and then run it. So the entire infrastructure you have for data acquisition, data persistence, and data processing, when you're actually processing the data, because as I mentioned earlier, to eliminate the seasonality, you got to process the data, and this has to be fast. For example, here in this model, it's predicting on a daily basis. But what if on an aircraft, you have to predict maybe every minute or every second, maybe a few seconds, if the machine is going to work fine or not. In Hexagon, we have an extremely fine-tuned machine called CMM, Coordinate Measurement Machine, which can measure the dimension of any component, and the tolerance levels are in microns. So it has a probe which actually touches the component and then measures. And if you're talking about micron level accuracy, the probe is actually coming fast enough to the component, but when it comes close enough to the component, it slows down and then touches very, very gently and then keeps on doing it. But remember, every time the probe touches, it's touching with some force. It could be minute force, but it's force. And because we're talking about micron level accuracy levels, after 10 measurements, 100 measurements, maybe 1,000 measurements, the probe is not any more accurate. A micron of tolerance levels, I think is the machine is not good anymore. I think we're talking about $500,000, $250K to $500,000 cost machines. So how would you predict? Maybe you want to predict when it's going to go off tolerance every 10 seconds maybe, or every minute maybe, I don't know. So if the machine, if you're having a model which is predicting fast enough, not only the data being acquired, it has to be fast enough, storing fault tolerantly, and then processing also has to be fast enough. Similar, another solution, another approach of explaining how it's extremely important, as I mentioned earlier, an aircraft, it actually creates 1 terabyte of data in one single flight. Having that information securely transferred to a central server, you actually can have a certain server in the aircraft to process and predict and signal to the pilots and other people, but you also have certain other data being transferred to a cloud for future processing. But here is the interesting part. You guys should read this paper. We are talking about predictive maintenance, where you can solve some of the predictive maintenance problems where if you know a component, a part need to be shipped, instead of shipping the part, the predictive maintenance model is going to detect which part need to be replaced, and it actually sends an order to a 3D printing machine which will print the part even at the aircraft where the aircraft is going to land, or at the airport where the aircraft is going to land, or somewhere nearby. So this is a good explanation of not just a predictive maintenance model, but how using IoT technologies, you are actually solving the real problem. That is, if something is going to fail, how do I know upfront, and then how do I fix it? And especially if the fixing is by replacing of a component or a part, get that part to the aircraft fast enough using 3D printers in this case. The best slide in my presentation. That's all I wanted to talk about today. If you have any questions, I'll be happy to answer.
Thank you very
Oh,
much.
thank you. Thank you.
Such an interesting talk. So we will have a question and answer session now. We have roughly 20-25 minutes from now onwards. So anyone who has questions?
We don't have to take the 20 minutes, right? Maybe if you have only 2 questions, I think we are done with that after that. After that, you can leave.
I have a lot more questions.
Okay. Yeah.
So,
Yes.
I have a few questions. Thank you for your interesting talk. The first question is about the battery analysis slide before the Turkish Electricity data.
Hmm?
Can you tell a little bit more about that study?
This is more of an example. I was trying to show the complexity of any predictive maintenance in an industry, in an IoT type of situation, where this is just if you have thousands of batteries, even for example, in the United States we have electric cars, Tesla you would have heard, and there are multiple batteries in the car, just not one. I think there are thousands of batteries, and there are sensors for each battery which is collecting information, and then it's detecting what's happening. And similar situation could be in a factory environment too. You have so many batteries which are giving sensors. But just want to show you the complexity of it. But in the Turkish electricity is where the consumption of electricity was what the focus of this study, and more information at the website. But if you want to make a prediction of what's going to happen in future in terms of your demand prediction, if you're a retail company, you can predict how many of your products are going to be bought. But in this case, it's going to be how much of the electricity is going to be consumed by my consumers in the future. And I was trying to highlight how complex it is. If you just look at the graph of the weekly consumption, the daily consumption, it's no way we can predict it. Just know if you do a linear regression, or if you just draw a simple straight line and say, okay, fine, the demand is going up. If you just draw a simple line, there's no way, if your line hits this point here, look at the error rate. It could be as high as this, or as low as this. You can't have unintelligent prediction and then make accommodation for that. So this research talks about using multiple machine learning models, how you can make a good prediction. And also the best part of this model or this study is this distinctly proves that I think a single technique would not be the solution all the time. Majority of the times, in my experience of machine learning solutions, very, very rarely we used a single technique to make a prediction or classification or detection, whatever it is. It always has to be an ensemble. And that's what this research proves.
And that brings to my second question. Since you mentioned, because one of my projects is also in industry IoT, so it's very similar to the battery issue, where we need to analyze a system, where it's a pretty new system. So all the data we have is positive value.
Mm-hmm.
Very few failure or negative cases. This is one challenge. And another thing is we want to know the holistic, the overview, the health status of the whole system from the components. And we have components, sensor, like the sensor information. So one solution I have is like the tensor approach, where we can have a vector, like a vector to present the component level, and then the whole vector can be ranking at the system level.
Sure. Yeah.
Can you think about or suggest other approach for like this particular study?
With the information you're giving, this could be a use case for using deep learning, neural networks, where you have a large amount of data that's coming in, you can feed in. In predictive maintenance, because it's a time series information, always, you got to feed in the information over a period of time. There is a technique called LSTM or RNN, recurrent neural network. But RNNs or LSTMs actually have limited memory. You got to be cautious in how much of data you can feed into the model before it starts forgetting what you've told earlier versus later. But if you can solve that, well, I can solve I don't know how to solve it, but we are a different company, so I cannot do the advising part. But if you do the neural network and use some variation of RNN LSTM to do the time series part of it, you can. That's number one. Number two, at a component level versus at the holistic machine level or the system level, you got to have different metrics. And if the moment you have a metric, a measurement on what you think is the indicator of health, it could be as simple as red light and a green light or whatever. It's a little more complicated than that. Once you define a metric, you will be able to identify the use case, and you will be able to identify the machine learning model, and then tell the model to predict that will satisfy your metric. So you got to start with the metrics first. So the component level, the metric has to be if it's consuming electricity or if it's on or off. But at the system level, you need to have different metrics too. That's all I can talk, but I think it's a lot more complicated than that, as you can imagine. If you buy me a drink, I think I'll tell you more information. But now I'm leaving today itself, but I was just joking. Thanks, yeah.
Thank you.
Any other question, please? No?
You know, there are only two reasons why you don't have any questions, except that gentleman. Reason number one is I was so brilliant. I was so fantastic.
You understood everything.
That's one reason. Second reason was,
There's a coffee break after.
no, nothing what I said made sense. But anyway, if you don't have any questions.
I have a question regarding one of your case study on the real-time data sets, like on the time series. You mentioned about the seasonality impact in one of your time series analysis. I was just wondering, when you were speaking about the seasonality impact, how could you differentiate that this particular peak in the graph is because of the seasonality impact, or this is some kind of anomaly in your data? That's why you're getting that bigger peak in your data sets.
Good question. Seasonality is one of the factors, and I'll explain how you can figure out. Abnormality is another factor too. For example, as I mentioned, in the electricity consumption, if a grid was down, or there was a major festival and hence there was more electricity consumption, the abnormality is, if you find a peak like this, for example, let's say you're looking at this data and said, how do I know if this is normal or this is an abnormal drop? The answer for the question is very, very simple, common sense, where you start looking at what happened. You start digging and talking to the SMEs, the subject matter experts or domain experts, or even just looking at the newspapers and finding out what was the reason why there was a drop, or what was the reason why there was a spike. For example, if you see the spike here compared to the previous week or whatever, you see a spike here, you would normally ask the questions. There are a few mathematical techniques which let's say every Monday there is a drop in the electricity consumption compared to a Sunday, and if you found that consistent variation, but on one specific Monday, instead of a drop, it actually went up, you normally go check, find out the SMEs or domain experts to find out what the reason could be. And if there is no specific answer, then maybe you would leave it as is, maybe that's a regular consumption. But if you find a very specific answer, yes, there was a breakdown, yes, there was a holiday, yes, there was a extraneous situation, or they want a government declared holiday, whatever, then you would know that's a spike or that's an abnormality, and then you take it off.
It's more like a subjective study.
It's more of a personal evaluation to look into the data and find out, and you need to ask questions. See, for example, here the graph which I'm showing is just a simple graph in a two-dimensional graph. But if you look at this data in an Excel sheet, this runs into thousands or even hundreds of thousands of columns of information, and you can actually go up and down. That's what I think data scientists do. Data scientists are those people who normally fall in love with the data. If you don't know who to love the data, and then you become a data scientist. That's what it is. So if you look at this thousands or millions of cells in your Excel sheet, and you will start looking at it and you start finding some patterns, and you actually have your own thumb rules on running some analytics to see, is there any consistent variation on a daily basis, an hourly basis, on a weekly basis, Monday versus Sunday, Monday versus Thursday, and you try to do all of these combinations and then find out what seems to be normal, what is not normal.
Right. Okay. Last question.
In your presentation, when you were talking about the case studies, you alluded to construction, but then there was not much details. Can you touch upon that?
So this image processing use case I was talking about, these two use cases are in the construction. For example, I think in one of the use cases I think we have in the company is, there was one customer wanted to find out, there are hundreds of people working in my construction site. I want to know if there is a unsafe behavior that's happening now. And the unsafe behavior can be anything. For example, a truck coming in and there is a worker who did not observe there's a truck is coming in. Or there is a crane which is lifting something and it's on a loose, out of the 3 hinges, 2 hinges are loose and it's going to fall. How would you know this? There is no single definition of abnormality. So one solution is where you can have a surveillance camera which is watching everything, and then it's constantly predicting what the next frame is. This is what is happening in this model, and there are a couple of other papers I've not shared today. There are good deep learning solutions available today which will predict what's going to happen in the next frame or next 2 frames. Or maybe next 100 frames, because next 1 or 2 frames is milliseconds. But if it's a 100 frame or next 1 minute, the model is constantly consuming what is watching and then figures out what is unexpected and then alerts people. So that use case could be satisfied using this type of solution. So any use case, even I talked about detecting a defective product or detecting a component which is misaligned. Let's say you're a car manufacturing company, you're setting up tires or wheels to the car, but something is not aligned well there. Anything today in an industry 4.0 situations where workers, expert workers, can look up with their naked eye and say, you know what, something is wrong there. You cannot replicate that knowledge, but you can train AI models which can look at using a camera and figure out, something is wrong there, which is what I think people are trying to look for now, because there is no standard definition of what is wrong. Things change too. For example, in that X-ray scanning here, the more you put in rules and regulations, if someone really wants to break, let's say a bad person, once you know what those are, you can circumvent those processes and do something new. So you cannot have a model which is defined on only a few specific definitions of what is wrong. The model has to constantly learn, and the definition of wrong also has to be vague enough the model can really understand faster. So if you abstract that problem statement to a construction site or a factory situation or a smart city on the roads or individual components in a factory, you can have an AI model which can detect what's going to go wrong in the near future.
One last question. You want to ask?
Maybe same kind of question too. In case of many attributes, you can predict anomalies based on the data. And how can you specify which attribute is the main cause of anomaly?
Yeah. That area of study is called feature engineering. So if you have, in this example, I think in this vehicle, where is the vehicle? Anyway, there were 104 types of measurements coming from each vehicle. But they've found out that not all 104 are required in the first place. In that specific example, they did something called PCA, Principal Component Analysis. You break it down, and then you find out which of these factors are having a major influence, and they brought it down to 20. PCA is one of the techniques. There are so many different other techniques too. In deep learning, some of the models automatically do feature engineering. My favorite argument, a comparison between machine learning and deep learning is, you have to do a lot of feature engineering in machine learning, and for deep learning, you don't have to do as much. You still have to do a little bit, but you can ignore that part. Of late, there is another area of research called explainable machine learning. When you know a machine is going to break down, let's say your car is going to break down, but just telling the car is going to break down is of no use unless you tell me, oh, the brake is actually failing, and hence go replace the brake. What's the use of telling me a machine is going to break down? I still have to have an expert come and look at the machine and then figure out what's happening. So explainable machine learning is a technique which we AI scientists are using nowadays, not only figure out what the end outcome is, but also find out how you arrived at the outcome. So feature engineering and explainable machine learning are two different techniques, but both will go to answer your question on which factors need to be considered. And out of these factors, not all factors will have the same impact. Some, let's say out of 100, you brought it down to 20. But of the 20, maybe 1, 4, and 8 may have a higher impact on the outcome than 3 and 7 and something. So even that relative impact of each factor could be analyzed doing feature engineering, and also, of course, a little bit of explainable machine learning techniques.
Thank you very much, SK. Just one last thing for the sake of myself and for the audience as well. If they really want to see your slides later on, is there any place they can download your slides from, or?
I can send the PDF version of it to the organizer here, yourself or to you, and maybe you can, whatever way the other speakers are allowing their slides, I think we can do the same thing.
Maybe once SK is going to send it to me, please email me whoever wants to get a copy of that, and I will forward it to you guys. And you already know the contact details of SK, and then you can
There's one data point I think I want to really mention. For those people who want to really learn more about AI and machine learning, I have a YouTube channel and I have lots of videos I post there, and there's a lot of different topics: deep learning, machine learning, smart cities, image processing, and so many different techniques. So you're welcome to check those videos too.
Thank you very much.
Thank you very much. Thanks. Thanks. Thank you very much. Thanks.